Welcome back, guys. I'm here with you to solve this problem number 21 of CSIR Net December 2017. So let us read it. Let Z denote the set of integers and Z greater than equal to 0. This symbol actually denotes the set of positive integers including 0. Now it says consider the map. So this is your map given by fmn is equal to this formula. Then the map f is. So in your options, what you have to do, you have to check whether your map is injective or surjective or both. Okay, so these are your options. So without going into the options, I will firstly write the map. So this is your map, right? Now see, fmn is given by 2 to the power m 2n plus 1, right? Now see this number. Can this number be 0? Does there exist m or n such that this number is 0? Suppose this number is 0. Okay, we need to find m and n such that this number is 0. Now since this is never 0 for any value of m, okay, m you are taking from z greater than equal to 0, that means set of positive integers, right? So this number can never be 0, that means 2n plus 1 is 0, that means n is equal to minus 1 over 2. So does this n belongs to z? No, this n does not belongs to z. That means no, for any m or n, this number is never 0. Okay, for no m, or I will say for no m comma n, this number is never going to be 0. You are getting my point or not? So this means there does not exist m comma n such that fmn is equal to 0, where m comma n belongs to z greater than 0 cross z. This is what is given to you. Okay, so from here what you can conclude, that 0 will never come in the image of this f. That means 0 does not have a pre-image. This is what we can conclude. So since 0 has no pre-image, so from here what you can conclude? You can conclude that this map is actually not surjective. Okay, now let us check injectivity of this map, right? So I will erase this thing. So not onto. So your first option says it is onto, therefore it is wrong. Okay, now your third option also says that both 1 1 and onto, so this is also wrong. Now you have to mark one of one between them, second and fourth. So for that matter you need to check whether it is 1 1 or onto, right? So checking injectivity, right? This is what I am checking right now. Now suppose that there exists, okay, so m1 comma n1 is equal to m2 comma n2, where m1, okay, where m1 comma n1 is not equal to m2 comma n2. Okay, so if you are writing this thing, what can be concluded from here? There are three cases you can conclude from here. The first one, that m1 is equal to m2 but n1 is not equal to n2. You are getting my point? Still this inequality will hold. Now second case, you can conclude that m1 is not equal to m2 but n1 is equal to n2. This is what you can conclude, right? Now come to the third one. You can conclude that both are unequal. Not but, I will use and here. You are getting my point or not? This tuple, okay, this coordinate is not equal to this coordinate. That means either this is not equal to this, or this is not equal to this, or both are unequal. These are the three cases that you can generate from here. Okay, now let us take your case number 1. Suppose m1 is equal to m2 and n1 is not equal to n2. So now by using this thing, this one, what you can write? You can write 2 to the power m. I will write m here, okay, instead of m1, because they are both are equal. I can do that. You are getting my point or not? I am not writing m1 m2 here because I am taking the case where both are equal, therefore I am writing just m. So this will be cancelled by this thing. So from here what you will get, n1 is equal to n2. So we are done. You are getting my point? We are done in this case. So 1 1 in this case. Now case number 2, suppose m1 is not equal to m2 and n1 is equal to n2. Okay, then what will happen? Okay, see, I will write n here instead of n1, okay, because they are equal. Now this number is non-zero, so they are equal, so you can cancel. Okay, you can only cancel because they are non-zero. Now 2 to the power m1 is equal to 2 to the power m2. So just apply log both sides, you will get what? You will get m1 is equal to m2. Are you getting my point? So these are the two easy cases. Okay, so in this case 1 1 again. Now we are left with the third case. The third one is little bit tricky, so I will write that thing now. So firstly I will erase. Okay, now I will write down the third case here. Suppose m1 is not equal to m2 and n1 is not equal to n2. Both are happening at the same time. Now since they are unequal, so without loss of generality, what I can say? I can say, let us suppose m1 is less than equal to m2. Okay, they cannot be equal, therefore I have to remove this one. Since they are unequal, so at least one of them has to be less than the other one. You are getting my point? So without loss of generality, I am taking that m1 is less than m2. Now write the condition. This one is the condition. Okay, so what you will get, 2 to the power m1 2n1 plus 1 is equal to 2 to the power m2 2n2 plus 1. Okay, so since m1 is less than m2, you can do 2n1 plus 1 is equal to 2 m2 minus m1, and 2n2 plus 1 is still there, right? You are getting my point or not? Okay, now see, for any n you choose, not any n, for any n1 you choose, this number is always a odd number. Okay, this number is always a odd number. Now since m2 is not equal to m1, therefore this is a multiple of 2. So this number is a even number. You are getting my point or not? So from here what you can conclude? You can conclude that this is a contradiction, because you are getting this odd number to be equal to this even number. You are getting my point or not? Okay, so I will repeat it again. What I have done, I have taken, because they are unequal, so I have taken without loss of generality that m1 is less than m2. Now use the condition for injectivity. So I have written down the condition. Now using this I am getting this thing. Now since m2 is bigger, so I can divide it with 2 to the power m1. So I have done that. Now see, since m2 is not equal to m1, therefore this number is a multiple of 2. This number being multiple of 2 is even, but for any n1 this number is odd. So you are getting a contradiction there. Are you getting or not? So this is a trick here to check whether, so that means from here what you are getting, that means you cannot take both m1 m2 unequal and n1 n2 unequal such that they are equal. You are getting my point? Therefore by contradiction this is 1 1. So hence we proved that this given function is always 1 1. Okay, so the fourth one is incorrect, therefore second one has to be correct, that it is 1 1 but not on 2, right? So thank you guys. Read this question. This is a question from analysis and it is basically based on the countability and uncountability of sets. So let us read it. Let a is equal to x square such that x is between 0 and 1, b is equal to x cube such that x is between 1 and 2, then which of the following statement is true? So first statement says there is a 1 1 on 2 function from a to b. Second one says there is no 1 1 on 2 function from a to b taking rationals to rationals. Third one says there is no 1 1 function from a to b which is onto. Fourth one says there is no onto function from a to b which is 1 1. Okay, so firstly what we should do, firstly we should see what are our sets a and b, how they look. So you see A is given by x square such that 0 to x less than 1. What I will do, I will take a map, okay, from this open interval to 0 1 and given by if x is equal to x square, okay. And for the B set, what is your B set? B set actually says that x is between 1 and 2, then you will get x cube. Now take a G map from this given set 1 2 to 1 8, okay, defined by gx is equal to x cube. So you have these two maps, right? So what is the important thing that you can notice from here? The important thing that you can notice from here that these maps are actually bijections, okay. These maps are actually bijections between 0 1 0 1 and 0 1, and this one is between 1 and 2 and 188. You are getting my point? So this is a little bit exercise for you. I'm not going to prove why they are bijections. This is what you can do yourself. So this is what you have to prove yourself, okay. So prove that this map is actually a bijection, okay. So from here what you are getting, that image of f under this set is actually 0 1. That means what is your A? A is actually 0 1. And what is your B? B is actually 1 8, because the image of this set, what is the image? It's 1 8 and it's a bijective image, okay. Now so you have 0 1 and B as 1 8. So these are the two open intervals that you have, okay. Now question is asking about a map between A and B. So the first option says there is 1 1 on 2 function from A to B. So for this option I am going to show you an important result in countability and uncountability topic, okay, in set countability of sets. So this is a very important result, okay. We can prove this result actually. So you see it says any two open interval of RD, okay, R is the real line and D is the usual metric, okay. Usual metric means the modulus that you take, mod. So any two open interval of RD are homeomorphic. So what is the meaning of this term homeomorphic? The meaning of this term homeomorphic is actually that there exists a continuous bijection, okay. So let us suppose you have two intervals taken. So it says if you are saying that the two intervals that you are taking are homeomorphic, then it says that there exists a continuous bijection f with f inverse continuous between two given open interval, okay. So A is said to be homeomorphic to B if there exists a continuous, okay, bijection between these two sets with f inverse also continuous, okay. This is the meaning of homeomorphic, okay. So what your question, what your theorem suggests us that between any two interval you can get these kind of homeomorphism. You're getting my point? So since A and B are open, A and B are open intervals. So what does that mean to you? It means there will exist a bijection, okay. So I am going to show you exactly what is that bijection, okay. So let us suppose, okay, I am going to erase the previous one, okay. I will keep this thing here and I will erase everything that I have written. Till now what we have done, we have just computed what is A and what is B. So A is your set 0 1 and B is your set 1 8, okay. Now according to this theorem, okay, this theorem says that between any two open interval of R and D they are homeomorphic. That means there exists a continuous bijection between them. So between these two sets you will get a bijection f, okay. So firstly I will tick the correct one and after that I will show what is that bijection, that continuous bijection, okay. I will write that continuous bijection for you. So first one says there is a 1 1 on 2 function from A to B. So from this theorem it is directly clear that its first is correct. Now it's a single correct option, okay. So therefore every option that is remaining there is incorrect, okay. Now let us say you have two open interval AB and CD. I am going to show you what is the bijection between these two, okay. So the bijection is given by d minus c over b minus a dot x minus a plus c. Okay, you don't have to remember this. I can show you a method how can you remember this. Okay, so you have AB and CD. Okay, I'm giving you a trick to remember this. So just consider these as your two coordinates in r square and these two coordinate in r square. Now let us suppose these are the 2 points in r square. You just have to draw a line between them. Okay, so what is the line between these two coordinates? Y minus c is equal to d minus c upon b minus a, that is the slope of the line, into x minus a. Okay, this is the line. Y is equal to d minus c upon b minus a, x minus a plus c. This is your line. Okay, and you see this is the map I am taking. So this is a line between AB and CD. Okay, therefore it's a bijection. This is a bijection, and if you will try to compute its inverse, you will also know that this is a bijection. This is a line, therefore it's continuous. So what I am saying, that if you will try to find out the inverse, you can do it yourself. That inverse will also be continuous. Okay, but that has no meaning in this question. You don't need f inverse to be continuous. It just says there exists a bijection. Okay, 1 1 onto map. So this is the map that you have to take between any two intervals to show them that they are homeomorphic. So what is the meaning of homeomorphic? I am repeating it again. AB, the interval AB and CD is said to be homeomorphic if there exists a bijection, continuous bijection f with f inverse continuous between them. You are getting my point? Now see what your second option says. It says there is no 1 1 onto function from A to B which take rationals to a rational number. Okay, so if you choose a rational bit from here, you will end up with a rational here also by this map, because this is a line. Okay, what I am saying, this is a bijection between these two intervals AB and CD. You can take your A0, B1 and C1 and D8. Okay, now if you will choose a rational from here, you will again get a rational. Okay, because this is a line. Okay, so you will get a rational. Therefore this option is false, because you have a map that takes rational to rational and it's a bijection. So it says there is no 1 1 onto function, but you are getting a 1 1 onto function that will take rational to rational. Therefore second option is false. Now come back for the third one. It says there is no 1 1 function from A to B which is onto, but it's so incorrect because you are getting it. Fourth one says there is no onto function from A to B which is 1 1, so you are getting it. Therefore fourth is also false. Okay, so this is a very easy question. All is dependent on this theorem and this map. Okay, if you remember this map, I told you. Okay, I told you how to remember this map. Just consider these two as our coordinates in R square and draw a line between them. You will always get a map. Okay, and this is not true only for the open interval. This is also true for the closed interval. If you will choose A, B, C, D to be your closed interval, then you will work with the same map and you will get the correct answer. Okay, so thank you guys.
See, it's a problem of analysis. Let us have a look. Which of the following set are uncountable? The set of all functions from R to 0, 1, the set of all functions from N to 0, 1, the set of all functions or all finite subsets of N, the set of all subsets of N. So you have these things in your hand. This question is totally based on upon the results. Right, so you don't have to use any brain here, or neither I am going to show you any proof of anything. I will just show you direct statement results, and using that we will directly solve it. All right, so proving these options are it's a little bit long process, so that is why I don't want to prove them here, because it's a solution video. If you are preparing for CSIR net, you must remember these statements. All right, otherwise you have no chance to solve this problem if you don't remember anything. All right, so that is why I will show you direct statements. Now see, we have these three notes that you have to remember. The third statement tells us that set of all subsets. All right, so we are talking about finite subsets here. So set of all finite subsets of natural number is countable. Not only countable, it is countably infinite. All right, so infinite. So it's countably infinite, that you have to remember. So because this is true, that means question was asking that which of the following set are uncountable, and here they have written that the set of all finite subsets of N is uncountable. It means third is incorrect. Now, fourth one tells us that the set of all subsets of n. Set of all subsets of n actually means the power set of natural number. So because of this statement, we know that power set of natural number is uncountable. So it means fourth is true. Now, this statement tells us that f such that f is a function from n to 0, 1 is uncountable. Are you getting my point? So if we have this kind of a statement that f we are collecting all those functions such that f is a function from n to 0, 1, then we know according to this statement that it is uncountable. So according to this statement, second will be true. So alright, so using these statement, what we will have that second is true. Now I want to show using this result, this first result, that first one is true. Alright, so 1/4 you can mark as correct, third will be incorrect. You have to now mark the first one whether it is true or not. So what I want to tell you is a very basic fact that if you have a function, alright, let us say you have a function from the set A to the set B, let us say, and you have two elements over here and you have, let us say, three elements. Now what do you know about the total number of functions? Alright, if you want to calculate total number of functions from here to here, we know that in case of finite set, it is actually total number of functions is actually B number of element inside B to the power number of element inside A. This is number of functions. Are you getting my point? So this is number of functions from A to B. Alright, cardinality of B to the power cardinality of A. Now what I want to tell you is this: when you will increase one element to it, what will happen? You will have more number of functions. Why? Because of this function, because of this formula, or you can also see with the basic thing. So if you will have more element in the domain, what will happen? Number of functions will always increase, alright, whether it is finite or it is infinite. In case of infinite, we don't know what cardinality we will have for the number of function, but what we know is it is the basic fact that if you will increase an element, then what will happen? The number of functions will increase. Let us see how. So suppose we have these three elements. So initially what you are doing, you are mapping two elements to these three elements. So maybe there is a possibility that you map like this. Now there will be two possibility because of this. What we will have another possibility also. Let us say you will map this to this and this to this. So are you getting my point or not? So if you will increase an element, the total number of functions will also increase. We know that functions from this set of natural number to 0, 1 is uncountable. We know? Yes, we know. Now if I replace this set of natural number with R, what we are doing is we are increasing number of elements inside the domain. That means the cardinality of this set, cardinality of f such that f is a function from n to 0, 1, the cardinality of this set will always be less than equal to the cardinality of f such that R to 0, 1. Are you getting my point or not? So because this was uncountable, so it has to be uncountable. It means that the first one is also correct. So 1, 2 and 4 are the answer for this problem. It's a easy problem, so I cannot explain anything more because these are the standard result. Alright, if you have understood everything from the analysis, these are the standard results that you can remember. Alright, so even if you don't remember proof in the exam, it's okay. Alright, nobody remember proof of everything. Alright, so even if you are good in mathematics, it doesn't mean that you will remember all the proofs. You can just remember the statement, and somehow if you will try, you will get your proof. Alright, so if you have any doubt, you can always ask in the comment section. If you have any other doubt, you can join our WhatsApp and Telegram groups. Links are given in the description part of the video. Alright, so thank you.
Number 61 of your part C of real analysis. So let us have a look on this problem. विच ऑफ द फॉलोइंग सेट्स आर इन बाइजेक्शन विद आर। तो बाइजेक्शन इन आर विद आर का क्या मीनिंग है कि इन सेट्स में से कौन बाइजेक्टिव मैप रखता है आर के साथ। ऑलराइट, तो वैसे आपको फॉर्मली यहां पर कोई बाइजेक्टिव मैप नहीं लिख के दिखाना है कि आपके पास ये बाइजेक्टिव मैप होगा, आप बिना उसके भी यहां पर कंक्लूड कर सकते हो। तो मैं 2 स्टेटमेंट्स लिखूंगा और उन दोनों स्टेटमेंट्स के बेसिस पर मैं इस प्रॉब्लम को सॉल्व कर दूंगा। ठीक है, तो लिखते हैं। तो नोट नंबर 1 मैंने ये लिखा है कि लेट ए एंड बी बी 2 सेट्स, देन वी से cardinality of A is same as cardinality of B if and only if there exists a bijective map in between them. Now B statement मैंने लिखी है Cantor's theorem, जो कि well known results है set theory में। let A be a set, then there does not exist any surjection from A to power set of A। तो A से power set of A पर कोई भी surjection कभी exist नहीं कर सकती। अब आपके पास जो सेट क्वेश्चन ने गिवन दिया है वो सेट ऑफ रियल नंबर्स है। ठीक है, तो सबसे पहले तो मैं डी ऑप्शन को यहां पर डिस्कार्ड करूंगा। तो डी ऑप्शन कह रहा है कि सेट ऑफ ऑल सबसेट्स ऑफ आर। इट मींस डी ऑप्शन में जो सेट है वो कौन सा सेट है, वो पावर सेट है। सेट ऑफ ऑल सबसेट्स ऑफ आर जो है वो पावर सेट ऑफ आर है। राइट, नाउ बाय कैंटर्स थ्योरम there does not exist f from R to power set of R a surjection। ठीक है, a surjection, तो कोई सर्जेक्शन ही नहीं है, तो फिर बाइजेक्शन कहां से हो जाएगी। तो क्या लिखेंगे, there does not exist f R to power set of R a bijection। So it finally proves that set of all subsets of R do not have any bijection with R। तो कोई भी बाइजेक्शन इन दोनों के बीच में एग्जिस्ट नहीं करती है। therefore D स्टेटमेंट आई कैन डायरेक्टली मार्क एज इनकरेक्ट। तो D स्टेटमेंट जो है इनकरेक्ट है। नाउ A ऑप्शन पर आते हैं। तो A ऑप्शन को यहां पर लिखेंगे। ठीक है, A ऑप्शन ये है कि सेट ऑफ ऑल मैप्स फ्रॉम 0 1 टू ए नेचुरल नंबर। इट मीन्स कि आपके पास क्या है, ये 0 है, ये 1 है, राइट, और आपके पास यहां पर एक सेट ऑफ नेचुरल नंबर है। आपको टोटल फंक्शंस ढूंढने हैं। तो देखो 0 के पास कितनी चॉइसेस हैं, 0 जो एलिमेंट है वो किसी पर भी मैप हो सकता है। तो 0 के पास जो चॉइसेस हैं वो कार्डिनैलिटी ऑफ नेचुरल नंबर है। कार्डिनैलिटी ऑफ नेचुरल नंबर को हम क्या कहते हैं, कार्डिनैलिटी ऑफ नेचुरल नंबर को हम अलिफ नॉट कहते हैं। राइट, और 1 के पास कितनी चॉइसेस हैं, 1 के पास भी ठीक नेचुरल नंबर के बराबर चॉइसेस हैं। राइट, सो टोटल फंक्शंस जो आएंगे, टोटल फंक्शंस, वैसे तो मैं फॉर्मूला अभी लिख के दूंगा आपको, बट टोटल फंक्शंस अगर हम एक छोटे से केस में देखें तो हमें पता चल रहा है कि टोटल फंक्शंस उससे क्रिएट होंगे जिस पर 0 मैप हो रहा है और जिस पर 1 मैप हो रहा है। तो 0 के पास टोटल जो चॉइसेस हैं वो अलिफ नॉट चॉइसेस हैं, अलिफ नॉट एलिमेंट्स पर वो मैप हो सकता है। राइट, दिस इज द कार्डिनैलिटी ऑफ नेचुरल नंबर। सिमिलरली 1 के पास भी टोटल चॉइसेस कितनी है, नेचुरल नंबर के इक्वल है। सो टोटल फंक्शन इज टोटल चॉइसेस, ठीक है, ऑफ 0 and 1। ठीक है, तो टोटल चॉइसेस ऑफ 0 and 1 टू बी मैप्ड विद। तो जितनी चॉइसेस मैपिंग की 0 और 1 के पास होगी उतनी ही आपके पास आएगी। तो टोटल फंक्शन जो है अलिफ नॉट इंटू अलिफ नॉट आएगा, जिसे हम लिख सकते हैं अलिफ नॉट स्क्वायर। और आप जानते हो कि नेचुरल नंबर इंटू नेचुरल नंबर काउंटेबल होता है। कार्टेशियन प्रोडक्ट ऑफ 2 काउंटेबल सेट इज काउंटेबल। देयरफॉर ये किसके इक्वल आएगा, अलिफ नॉट के ही इक्वल आएगा। राइट, इट इज एक्चुअली द जो हम ये काम कर रहे हैं सारा का सारा, ये जस्ट एल्जेब्रा है इस नोटेशंस के साथ। ठीक है, तो अलिफ नॉट का स्क्वायर जो आता है वो अलिफ नॉट के इक्वल आता है। क्यों, क्योंकि हम जानते हैं कि नेचुरल नंबर क्रॉस नेचुरल नंबर, दैट मीन्स नेचुरल नंबर कार्टेशियन प्रोडक्ट विद नेचुरल नंबर इज अ काउंटेबल सेट। तो अलिफ नॉट आ गया जो कि क्या है, नेचुरल नंबर की कार्डिनैलिटी है। तो टोटल फंक्शंस जो हमारे पास आ रहे हैं इस सेट से इस सेट पर, वो कितने आ रहे हैं, जितने हमारे पास नेचुरल नंबर है। इट मींस इट्स अ काउंटेबल सेट, और काउंटेबल सेट और अनकाउंटेबल सेट के बीच में कोई भी मैपिंग नहीं एग्जिस्ट कर सकती, बाइजेक्टिव। सो देयर डज नॉट एग्जिस्ट एनी बाइजेक्टिव मैप फ्रॉम अ काउंटेबल सेट टू अ अनकाउंटेबल सेट। हेंस ए ऑप्शन यहां से इनकरेक्ट हो गया। तो ए ऑप्शन यहां से इनकरेक्ट हो गया। अब जो बी और सी ऑप्शन है ये एक्चुअली में ट्रू है। ठीक है, तो ये रिजल्ट है। यहां पर मैं 3rd नंबर का एक नोट आपके सामने लिख रहा हूं, डायरेक्टली मैं यहां पर एज अ नोट यहां पर लिख रहा हूं। सो नोट ये है कि कार्डिनलिटी ऑफ आर जो होता है अलिफ नॉट की टर्म्स में, या फिर चलो पहले लिखते हैं, तो ये पावर सेट ऑफ नेचुरल नंबर के इक्वल होता है। ये आपको याद रखना होता है। क्लासेस में जब आपके पास फॉर्मल कोई कोर्स चल रहा हो तो उसमें ये प्रूफ भी कर देते हैं कि पावर सेट ऑफ नेचुरल नंबर इज इक्विवेलेंट टू आर, और दोनों की जो कार्डिनलिटी है उसे रिप्रेजेंट करते हैं 2 टू द पावर अलिफ नॉट से। ठीक है, नाउ बी ऑप्शन को देखो। ये इससे हमें क्या पता चला? इससे हमें पता चला कि सी ऑप्शन तो ट्रू है, राइट? सो सी इज ट्रू फ्रॉम हेयर। नाउ मैं ये कहूंगा कि बी ऑप्शन इसलिए ट्रू है, उसके लिए मैं एक नोट लिखूंगा। नोट ये है कि चाहे सेट आपके पास फाइनाइट हो चाहे इनफाइनाइट हो, नंबर ऑफ फंक्शंस फ्रॉम a to b is equal to cardinality of b to the power cardinality of a। ठीक है, तो b की पावर में लिखा गया है कार्डिनलिटी ऑफ a, इवन इफ इट इज इनफाइनाइट देन ऑल्सो इट वर्क। ठीक है, तो अगर इनफाइनाइट भी है तब भी ये वर्क करेगा। तो b की कार्डिनलिटी कितनी है इस केस में? 2, और इसकी कार्डिनलिटी कितनी है? नेचुरल नंबर। इट मीन्स जो बी ऑप्शन में सेट दिया हुआ है उसकी कार्डिनलिटी कितनी है? उसकी कार्डिनलिटी है 2 टू द पावर अलिफ नॉट, क्योंकि ये 2 कार्डिनलिटी का है और ये अलिफ नॉट कार्डिनलिटी का है। आपको मैंने बताया था नोट नंबर 3 में कि रियल नंबर की कार्डिनलिटी 2 टू द पावर अलिफ नॉट ही होती है। इट मीन्स देयर इज अ बाइजेक्शन इन बिटवीन देम। सो दैट्स वाई बी एंड सी रिजल्ट्स आर ट्रू। आपको जस्ट ये एल्जेब्रा ध्यान रखना होता है किसके करस्पॉन्डिंग, जो आपके पास इन नंबर्स हैं, जैसे इनफाइनाइट सेट की जो कार्डिनलिटी है उनके ऊपर जो एल्जेब्रा है, थोड़ा बहुत उसके बारे में अगर आपको नॉलेज है तो आप बहुत जल्दी इस प्रॉब्लम को सॉल्व कर सकते हो। ऑलराइट, सो थैंक यू।
Question says which of the following sets are uncountable. The first one is the set of all functions from R to the set 0 1, the set of all functions from n to 0 1, and the set of all finite subsets of n, and fourth is the set of all subsets of n. So before solving this question, let me write some facts. Suppose A is any set having cardinality m, so let A is any set having cardinality m and B having cardinality n. So the total number of functions from A to B is, suppose this is the set A and this is set B. We have m elements x1 x2 up to xm, and here we have n elements y1 y2 up to yn. So the total number of functions from this set A to B can be determined. This x1 can be mapped to any of these y1 y2 up to yn. That means x1 have n possibilities. Similarly x2 have again n possibilities, and since it is a function, so every element of A should be mapped to B. So that means every element of set A have n different possibilities. So x1 has n possibilities, again this x2 has n possibilities, so up to m means xm also has n possibilities. So the total number of functions from A to B are n into n into n m times. That is the number of element in this set A times. So this is equal to n to the power m. So this is equal to n to the power m. That is cardinality of B to the power cardinality of A. So this is the total number of functions from set A to set B. Again we also know that total number of subsets of a set having n elements, that is the cardinality of the power set of a set having n elements is equal to 2 to the power n. This is the cardinality of power set of A, where cardinality of A is equal to n. So it is 2 to the power n. So we are going to use these two facts. So let us first see the option number 2, because natural number is a subset of real number. So if we can determine that number of functions from n to 0 1, then it will be easy to evaluate from r to 0 1. So option number 2, total number of functions, the set of all functions, the total number of functions from n to 0 1. From this formula we can see that the cardinality of n natural number is denoted by LF naught. So the total number of functions from n to 0 1 by this formula will be equal to, suppose a is equal to 0 1, so cardinality of a is equal to 2. So total number of cardinality of a to the power cardinality of n, which is equal to 2 to the power LF naught, and 2 to the power LF naught is equal to c, which is uncountable. C is uncountable. So the total number of functions from n to 0 1 is uncountable. So this option number 2 is correct. So if option number 2 is correct, 1 is automatically correct, because 2 implies 1. If 2 is correct, then 1 is correct, because first one is the superset of the second option. That is, suppose x is equal to f, such that f from n to 0 1 is a function, and y is equal to g, such that g from r to 0 1. This x is a set of all functions from n to 0 1, and g is y is a set of all functions from r to 0 1. So clearly we can see that x is a subset of y. Now if x is uncountable, then y is automatically uncountable. So option number 1 is also correct. Now we look at option number 3, which says the set of all finite subsets of n. So let x is equal to a, such that a subset of n, a is finite. So a is a finite subset of n. So we can write, let a is equal to x1 x2 up to xn, where n is a finite number. So since a is a finite set, so this x1 can be any natural number from the set of natural number. So x1 have number of possibilities. So we can write choice for x1 is equal to the cardinality of natural number, which is equal to LF naught. So similarly, choice for x2, this x2 again can be any of the natural number, so it is again cardinality of natural number, which is LF naught. So proceeding the same way, cardinality for choice for xn will also be equal to LF naught. So total possibilities of number of sets will be equal to of number of sets of x, we can write equal to the product of all these, that is times cardinality of n times, so which will be equal to cardinality of n to the power n, right, which is equal to again LF naught to the power n, which is actually the finite product of finite Cartesian product of countable sets, right? And we know that finite product of countable set is countable, so that means 3 is countable. So option 3 is incorrect. according to what means option 3 is incorrect. So now we'll look at option number 4, which says the total number of subsets of n. We know that cardinality of n is equal to LF naught, and the total number of subsets, that is the cardinality of power sets of n, will be equal to 2 to the power LF naught, which is by this formula, which is equal to C, that is uncountable. So it is uncountable. So option number 4 is also correct. So correct answer to this question are 1, 2 and 4. Thank you.
इक्वल टू द सेट कंटेनिंग एलिमेंट्स 1 टू अप टू 100. ए आपको ये सेट दिया गया है, बी ये सेट दिया गया है. देन बताना है व्हाट इज द टोटल नंबर ऑफ सबसेट्स ऑफ एस विच हैव नॉन एम्प्टी इंटरसेक्शन विद बोथ ए एंड बी. तो आपको वो सबसेट्स देखने हैं एस के जिनका इंटरसेक्शन ए के साथ भी नॉन एम्प्टी होना चाहिए एंड बी के साथ भी नॉन एम्प्टी होना चाहिए. तो ए के कुछ एलिमेंट भी उस सबसेट में होने चाहिए एंड बी के भी कुछ एलिमेंट्स उस सबसेट में होने चाहिए. तो अगर लेट्स से आपको ये देखना हो कि नंबर ऑफ एलिमेंट्स इस सेट में कितने हैं, तो आप क्या देख सकते हो, टोटल एलिमेंट्स देखो एंड वो एलिमेंट्स देखो जो ए में नहीं है, तो वो नंबर ऑफ एलिमेंट्स इन ए के बराबर आ जाएंगे. तो सेम चीज हम ये कह सकते हैं कि जो चीज हमें निकालनी है उसके लिए हम क्या कर सकते हैं, सबसे पहले देख सकते हैं टोटल सबसेट्स कितने हैं एस के. देन इस स्टेटमेंट का जो नेगेशन है वो हम लिख सकते हैं. इस स्टेटमेंट का अगर नेगेशन आप देखोगे तो क्या आएगा, नॉन एम्प्टी इंटरसेक्शन ए के साथ भी बी के साथ भी. नेगेशन क्या होगा कि एम्प्टी इंटरसेक्शन या तो ए के साथ या फिर बी के साथ. सो माइनस वो सबसेट्स, नंबर ऑफ सबसेट्स हैविंग एम्प्टी इंटरसेक्शन विद ए और बी. ओके, तो लेट से आपने एक सेट डिनोट किया S1, इस ये रिप्रेजेंट कर रहा है वो सबसेट्स जिनका इंटरसेक्शन ए के साथ एम्प्टी है, सबसेट्स विद एम्प्टी इंटरसेक्शन ए के साथ है. S2 वो सबसेट्स रिप्रेजेंट कर रहे हैं जिनका एम्प्टी इंटरसेक्शन बी के साथ है. तो यहाँ पे आपको क्या देखना है, एम्प्टी इंटरसेक्शन या तो ए के साथ या फिर बी के साथ. इट मीन सेट आपको इस सेट की कार्डिनलिटी देखनी है, एन ऑफ S1 यूनियन S2 क्या होगा. देन टोटल सबसेट्स ऑफ S में यहाँ पे देखते हैं, S में 100 एलिमेंट्स हैं, अगर किसी सेट में n एलिमेंट्स होते हैं तो टोटल सबसेट्स कितने आते हैं, 2 रेज़ टू पावर n. तो यहाँ पे टोटल सबसेट्स कितने आ जाएंगे, 2 रेज़ टू पावर 100. माइनस आपको क्या देखना है, n ऑफ S1 यूनियन S2 देखना है, जिसको हम लिख सकते हैं नंबर ऑफ एलिमेंट्स इन ए यूनियन बी क्या होता है, नंबर ऑफ एलिमेंट्स इन ए प्लस नंबर ऑफ एलिमेंट्स इन बी माइनस नंबर ऑफ एलिमेंट्स इन ए इंटरसेक्शन बी. तो ये बन जाएगा नंबर ऑफ एलिमेंट्स इन S1 प्लस नंबर ऑफ एलिमेंट्स इन S2 माइनस नंबर ऑफ एलिमेंट्स इन S1 इंटरसेक्शन S2. तो S1 है वो सबसेट्स जिनका इंटरसेक्शन ए के साथ एम्प्टी है. तो ए के साथ इंटरसेक्शन एम्प्टी होना चाहिए. इट मीन सेट 1 to 10 उन सबसेट में ये सारे एलिमेंट्स जो है वो आप कह सकते हो कि डेफिनेटली प्रेजेंट नहीं है. देन इनके पास 2 चॉइसेस है, 11 से लेके 100 तक. अगर आप देखो 11 या तो सबसेट में प्रेजेंट होगा या फिर प्रेजेंट नहीं होगा. तो इस एलिमेंट तो लेने के 2 वेज है, या तो लोडे या फिर नहीं लोडे. देन सेम फॉर 12, देन सेम फॉर 100. और जो बाकी ये 1 से 10 है, इन एलिमेंट के पास एक ही वे है कि इसको सबसेट में हम नहीं ले रहे. तो आपके पास यहाँ पे रूल ऑफ प्रोडक्ट से हम कह सकते हैं कि टोटल सबसेट्स कितने बनेंगे, 1 into 1 into 1 up to 10 times, 2 into 2 into 2 up to 90 times. So it will be 2 raised to power 90. तो n of S1 कितना आ जाएगा, 2 raised to power 90. देन वो सबसेट्स जिनका इंटरसेक्शन बी के साथ एम्प्टी है, बी में 10 एलिमेंट्स है, इन 10 एलिमेंट्स के पास यही चॉइस है कि इनको हमें सबसेट के अंदर नहीं लेना. टोटल एलिमेंट्स 100 है, तो आपके पास ये वाली सेट की कार्डिनलिटी कितनी आ जाएगी, 2 raised to power 90. देन n ऑफ S1 इंटरसेक्शन S2 वो सबसेट्स जिनका इंटरसेक्शन ए के साथ भी एम्प्टी है और बी के साथ भी एम्प्टी है. तो 1 से 10 तक ये एलिमेंट भी हमें नहीं लेने हैं सबसेट्स में, 41 से 50 के बीच में ये एलिमेंट्स भी हमें नहीं लेने हैं सबसेट के अंदर. तो बाकी बचे एलिमेंट्स कौन से हुए, 11 से 40 एंड 51 से 100। इन सभी एलिमेंट्स के पास टू वेज है, या तो आप इसको सबसेट में डालोगे या फिर सबसेट में नहीं डालोगे। तो आपके पास कितने बचे एलिमेंट्स कितने हुए, 80 हुए। तो टोटल सबसेट्स यहाँ से कितने आ जाएंगे, 2⁻80। एंड यहाँ पे आपके पास 2⁻100 है। अब इसको सॉल्व करेंगे तो आपके पास आएगा 2⁻100 माइनस इन दोनों टर्म्स को कंबाइन किया तो 2 इंटू 2⁻90 विच इज इक्वल टू 2⁻91। देन इसके बाद माइनस माइनस प्लस, देन आ रहा है 2⁻80। अब इन तीनों टर्म्स में आप देख सकते हो 2⁻80 कॉमन आ रहा है और अंदर बच रहा है 2⁻20 माइनस 2⁻11 प्लस 1। देन ये है 2⁻80 ब्रैकेट, ये है 2⁻10 का स्क्वेयर, ये है 1 का स्क्वेयर, ये है 2 इंटू ए इंटू बी। तो ये आपके पास a माइनस बी का स्क्वेयर बन रहा है। a इज 2⁻10, b इज 1 और इसका आप क्या कर रहे हो, स्क्वेयर कर रहे हो। तो अब आप देख सकते हो कौन सा ऑप्शन जो है वो मैच कर रहा है, ऑप्शन 3। तो इट मीन्स दैट 3 क्या है, ट्रू स्टेटमेंट है, बाकी सारे ऑप्शंस क्या होंगे, गलत होंगे। ओके,
a set theory question, or you can say analysis question. Okay, so let us read. Which of the following is necessarily true for a function f from x to y? So the first option says if f is injective, then there exists g such that y to x such that f of gy is equal to y for all y belongs to y. So this is your first option. Okay, I'm not going to read these next option before solving this. Okay, so I will firstly solve this and then I will go to the next option. It says, first option says if f is injective, then there exists g such that y to x. Okay, so in first option it is given to you that f is injective, right? What else information do you have for first option? That it is telling us that if f is injective, then you will get a g, okay, from y to x such that f of gy is equal to y. Okay, now by only this injectivity condition they are saying that you will get a guarantee of such kind of functions, right? So what I will take my x to be just a singleton set and y, not small y, the capital Y I will choose to be 1 and 2. Now let us consider f of function from x to y such that f of 1 is equal to 1. So from here 2 has 2, that element 2 which is inside y has no preimage. Okay, it is a 1 1 function but it is not on 2, right? So this function can actually satisfy your condition because it is injective, right? And it is a function from x to y. So all the condition, all the hypothesis that is given in the question is already satisfied. Now see, can there exist a y such that f of gy is equal to y for all y belonging to y? Can there exist? No, because if you will choose y to be 2, then this will mean that f of gy is equal to 2. But you see, whatever this quantity is, you don't, that doesn't matter because f has only, okay, 1 in its image. That means image of f, from here what this will guarantee that 2 belongs to image of f. That is not possible, right? Is it possible that 2 belongs to image of f? No, because image of f only contain one element, that is 1. So hence this existence of this function is never guaranteed from here. You are getting my point? There will no exist no such function such that this will give you 2. So therefore this statement is wrong by just taking this as my counter example, right? So first one is incorrect. Now I will directly go to the third one and then I will see fourth one. Okay, I will see second one later. So third one says if f is injective and y is countable, then x is finite. So do you think this is true? No, this cannot be true because if you will choose x and y to be equal and equal to natural number and you just take the identity map between them. Now this identity map is 1 1. Okay, this identity map is 1 1. Now since this is 1 1 and your y is also countable. Then x is finite, it says, but x is not finite, so therefore third one is incorrect. Now let us come to fourth one. Fourth one actually says if f is surjective and x is uncountable, then y is countable infinite. Do you think it is true? No, it's not true. Why? I can take a function from real to this singleton set by just taking fx is equal to 1 for all x. Now this function is well defined and surjective, therefore one has to be countable infinite by according to your fourth option. But it is not true. This is a singleton set, this is a finite set, it's not a countable infinite set. Therefore you are getting a contradiction. That means where is the problem? Problem is that what is given in your question, right? So this cannot be countable infinite for every case. So therefore fourth one is incorrect. Okay. Now first is incorrect, so that means your correct option will be 2. But now what I have to do, I have to prove this option, why this is correct. Okay. Now I will erase everything. So to discard first, third and fourth is very easy. In exam you can do just in 1 minute. Okay. You can discard these options and then mark for third, second as you are correct. But in exam you don't have to prove this, right? But I am proving it this second question to make it this video much more informative. That's why I am doing this question number 2. Now what I have to prove, that if f is surjective, right, then there exists g from y to x such that f of g of y is equal to y. This is what I am going to prove, right? So now firstly I am going to use this thing, what is given to you. It is given to you that f is surjective, right? That means pre-image of everything is there. Okay, so pre-image of everything is there, it is given to you. Now what is my strategy? Okay, strategy is very simple. Okay, I am just constructing this function g. What will be this function g? So I am considering my function g to be f inverse. Okay, what I am doing, I am considering my g to be a function which is denoted as f inverse, where f inverse is actually the pre-image, right? So I will firstly write, I am constructing this g for you. Okay, so just try to see this thing from here. G is a function from y to x. Now f inverse, okay, f inverse is actually, okay, I will firstly say f inverse y, I will denote this set as f inverse y as this will consist of all those x such that fx is equal to y. So f inverse y is actually a set for me, okay, set of pre-image, because what is happening there, firstly see this thing. Suppose this is x, this is y, and f is a surjective map between these two sets. Now let us suppose this is your y here. Okay, now it can have, since it is surjective, so every element here will have a pre-image, but this thing is not guaranteeing us that this function is 1 1. That means in the pre-image set you may get x1, x2, x3 and many more element, right? You are getting my point or not? So in the pre-image set, this set can have cardinality greater than 1, okay, because it is not given to you that this function is 1 1. So in your case f inverse y, the example that I am giving you, in your case, in this case, f inverse y will consist of x1, x2 and x3. This is your set, right? So this set will exist, this set is non-empty, right? This set is non-empty for every y. Why this is non-empty? Because it is given to you that your function is surjective. That's why it is non-empty. Now I am defining your g function, it is a function from y, so I am defining your g to be f inverse of y, okay, where the condition is that f inverse of y, okay, choose any element from f inverse y. Okay, I will not write f inverse y, then I will directly write g is a function from y to x. Now I am defining it like this, that g of y is equal to choose a single element from f inverse y. So image of y will be given by choosing any element from this set. You will choose any element from this set, okay, that will be image of y. You are getting my point or not? You can choose any element from here, okay. So this is the function g of y. Now see, is this function satisfying this criteria? Okay, I will prove this, the existence of this thing. I'm just firstly I'm giving you a hint how I'm proceeding. So now see, f of gy, f of gy is actually equal to, from this example, let us suppose f of xi. You are getting my point or not? You are choosing any element. So let us suppose I have chosen xi from there. So now see, what is f of xy? It is again y, okay, and this is happening for every y. You are getting my point or not? Think over it, that what I have done, how I have constructed this function g. I have constructed this function g by just choosing a single element from f inverse y. It doesn't matter which element you choose, but just you have to choose, okay. And now who will give guarantee that you can actually choose? Okay, now axiom of choice comes into the picture, okay. So this is the definition for axiom of choice. So what it says, that if A alpha is a non-empty indexed family of non-empty mutually disjoint sets, then there exists a non-empty set which contains exactly one element from each A alpha. You are getting my point or not? It says that A alpha is a non-empty indexed family of non-empty mutually disjoint. I have written, I think, no, it's correct. So let A alpha is a non-empty indexed family of non-empty mutually disjoint set. So what is your family in your case? Your family is this. Okay, I will repeat myself if you are getting confused. I am trying to construct this function. So I have given a definition for this function, that how to write this function. In this definition, I am choosing a single element from f inverse y. Whatever y you give me, I will choose an element from f inverse y, and then I will define this function, right? And I have proved that this function will actually satisfy this criteria. Now I am done. The only thing that is required to prove that actually I can choose this single element. Okay, who will give us guarantee that can you actually choose this element? This guarantee will be given by the axiom of choice. Okay, now see, what is this axiom of choice? It says that if A alpha, okay, this is a family. If A alpha is a family of non-empty indexed family, right, of non-empty mutually disjoint set, then there exists a non-empty set which contain exactly one element from each A alpha. Now what is your A alpha in your case? The A alpha that is in your case is f inverse of y. This is A alpha where y belongs to capital Y. Okay, this is the family that I am taking. Now using axiom of choice, I can construct a set which consists of exactly one element from each A alpha. So that's why I can choose this one. Okay, using axiom of choice you can do this. Okay, axiom of choice is coming into the picture for choosing this element. Okay, think over it, read this definition again. Firstly, think over it, that why all the conditions of this, all the hypotheses are being satisfied, that it is non-empty and mutually disjoint. You have to think over it, okay, because this will make this video a little bit longer, but think it yourself. Why I am using axiom of choice, I have already told you, but if you are not getting it, then you should think it properly, okay, in a proper sense, because this is mathematics. For every statement you have to give some certain logic or argument in order to make sense of that argument, in order to make sense of that statement, right? So this is the way of creating this G. So second one, therefore it is correct. Okay, so I will repeat quickly. It is given to us that f is surjective, then it says there exists G such that this thing will happen. I have constructed this G using this definition and I am done. But in order to construct that definition, you need to use axiom of choice. Okay, so think over it, that why I have used axiom of choice. It's your duty, because this is mathematics. Everything I cannot teach you. Something you have to think in your mind, and then after that you will get satisfied. Okay, I will speak for about 1 hour, then still it can happen that you are not getting satisfied. But the only thing that will make you satisfy is that you think over it yourself. This is very important to think over it. Okay, proofs are always important in mathematics. Okay, without these proofs, if you will try to remember theorems and that all, you will not get success from that thing. You have to remember, remembering theorem is good, right? I'm not saying that remembering theorem is not good, but it can help you up to some extent. You cannot always solve a question using remembering a theorem and then applying it and then solving it. You cannot do every time. You cannot do that every time. You have to go over proofs, certain proofs like this, okay, and then try to formulate a argument for you. Try to formulate a proof, okay, which consists of logical argument, and try to think over it that why it is correct yourself. Okay, now you are a teacher, now you have to think over it that why it is correct. Just try to learn mathematics like that, then only you can think over it. Okay, so thank you guys. So let us read. It's a very easy question. Let S be an infinite, okay, there's a word missing here. Let S be an infinite set, then which of the following are true? Okay, so the first option says if there is an injection from a set S which is infinite to natural, then S is countable. Second one says that if there is a surjection from S to N, then S is countable. Third one says if there is an injection from N to S, then S is countable. And the fourth one says if there is a surjection from N to S, then S is countable. Okay, so before starting the question, I will just provide you a note that will help you to solve this question. So suppose, what I mean to say, that suppose f such that A to B, okay, be a surjective map, okay, then cardinality of B is always greater than or equal to cardinality of B. Okay, so this first number note says that if you have a surjective map, okay, in the case of finite, if A and B are both finite, then you can talk about the cardinality. Okay, this will be a little bit abusing of the notation that cardinality works only for the finite set, but you can say for the exam purpose that if A to B is a surjective map, then number of element in A is must always be greater than, okay, so you can say that A will always have more number of element than in B if it is a surjective map. Okay, so this one this is the note first. Now for the note 2, suppose if such that A to B is injective, okay, then cardinality of A is always less than or equal to cardinality of P. Okay, I'm again saying for the infinite case it will be little bit abusing of the notations. Okay, cardinality will not work there, but you can take it as granted that if if f such that A to B is injective, then number of element in A must be greater. Okay, not greater, number of element in A must be less than number of element in B, that A will always have lesser number of element than B. Now come back to the question. What it says that if there is an injection from S to N, then S is countable. Okay, so from options first, what you see, there is an injection from S to N. So if f is an injection from S to N, that will directly imply from the note number 2 that cardinality of S is always less than cardinality of the natural. So this will imply S is countable. Okay, since it has cardinality less than or equal to the natural number. So first one is directly correct. Now come back to the fourth one. What it says that if there is a surjection from N to S, then S is countable. Okay, this one is the first option I'm checking. Now I'm checking the fourth one. Fourth one says if there is a surjection from N to S, then S is countable. So you see from the note number 1, that if f such that a to b is a surjective map, then cardinality of b is always greater than equal to the cardinality of a. A is must be so then the cardinality of b is always greater than or equal to the cardinality of a. So from the note number 4 you can say cardinality of n is greater than cardinality of s for the fourth option, and that will directly imply s is countable, since s has less number of elephant than the set of naturals. So fourth one is correct. Now this come back to the second one. Second one says that if there is a surjection from s to n, okay, from s to n there is a surjection, then s is countable. Okay, so if there is a surjection from s to n, then from note number 1 you can directly say that cardinality of s is greater than cardinality of natural number. So equal is also there, so you cannot say anything about that, okay, whether it will be countable or not. So let us take a counter example for it. Okay, so for the second option I am taking a counter example. So if you just take s equal to r and just take the map, okay, and just take the map like this. If okay, so fx is equal to x for all x belongs to naturals, and okay, I will partition the function into a multi-valued function. So fx works like this, belongs to r minus n. Okay, so for all real number which are not natural, I am sending them to 1. So you see this map is a surjective map, but s is not countable, so your second option is incorrect. Now coming back to the option number third. Option third says that if there is an injection from s to n to s, so they are saying that there is an injection from n to s, so from note number 2 you can conclude that cardinality of n is less than cardinality of s. Okay, so you cannot conclude anything about s because natural number has lesser or equal to cardinality of s, so s can be uncountable here. So for that matter I will just create an example. What you have to do, you have to create a injective map from n to s. Again take s is equal to r and take the function fx is equal to x for all x belongs to naturals. Okay, so take this as your function. I am considering s to be r. Now you see fx is equal to x, that means you are mapping natural to natural. So so you see this map is a injective map, but s is equal to r is not a countable set. So third is false and second is also false. So first and fourth are correct. Okay, so thank you guys. So let us read the question before we solve it. What question is asking that consider the map f such that q to r. So we have a map from the set of rationals to the set of reals defined by fx is equal to, when your entry is 0, when your x is 0, then the map will give you 0, and when your entry is in the form of p by q, where p belongs to integer and q belongs to natural number having the properties such that their GCD is 1, okay, greatest common divisor is 1, then map will give you the value p over 10 to the power q. So this is your map. Okay, so this is your map. Now what do you have to check? You have to check just the injectivity and surjectivity of this map. So I am dividing this video into two parts. One part will directly consist of the solution for this question. Okay, so I will use some theorems here, and I will just discard option and give you the correct answer, and the second part will contain the proof all those theorem which will be included in this solution part. Okay, so this video will consist of two part. Now I am just doing the first part. So what is given to us? It is given that f is a map from the set of rationals to the real, and it is given by fx is equal to 0 if x is 0, and if x, okay, So if you remember the definition of rationals, then you will notice that the whole thing that is written here is just the rational definition of the rationals. So I can directly write that if x belongs to q, but 0 is already used, so you have to subtract 0 from the set of rationals. So if x belongs to q minus 0, then your answer will be like this. Okay, you can just write it in short form. Now this is your map which you have to check that whether it is 1 1 or on 2. Okay, that you have to check. Now I will provide you some important properties regarding this, regarding injectivity and subjectivity. Okay, so that you must remember before solving this question. So I am writing a note here. Okay, so what this note tells you that if f is a function from the set A to the set B, with if f is a function from A to B such that f is onto, okay, so if f is a onto function from A to B, then cardinality of your domain, cardinality of A, that is your domain, is greater than equals to the cardinality of B. Okay, so if f is a onto function from A to B, then your cardinality of A is always greater than equal to the cardinality of B. Okay, so this is your first note. Now second note says that the set of rationals, okay, the set of rationals is countable, but the set of reals is uncountable. Now you have to use just these two notes and you will get your answer. Okay, so what is given to us, that f is a function from q to r. So firstly assume that f is onto. Okay, so suppose you have assumed that f is onto, then it will directly imply from the note number 1 that your cardinality of your domain, that is your rational number, is greater than cardinality of R. Okay, now from the note number 2 you see that rationals are countable and the set of reals is uncountable. That means the set of real has greater cardinality than the set of rationals. So from note 2 what you are getting, from note 2 you are getting that cardinality of R is greater than cardinality of Q. It is strictly greater because R is uncountable and Q is countable. Okay, so that will imply that we will get a contradiction, because you are assuming that your function is onto, then it will directly imply that cardinality of rational must be greater than cardinality of reals. But from note number 2 you are getting that your real has greater cardinality than the set of rationals. So it's a contradiction. So where is the mistake? Mistake is in our assumption. So you are assuming that your function is onto, so it is impossible for a function from the set of rational to the set of real to be onto. So that will directly imply f is not onto. Okay, so you can directly say that your function is not onto. Okay, or I can say that any function that is from the set of rationals to the set of real can never be a surjective function, because you will always get this type of contradiction here. Okay, so your function is not onto. So your option A is saying that your function is onto, so A option is false. Your B option is saying that your function is onto, so your B option is also false. Your C option still says that your function is onto, so your C option is also false. So you can directly say that it is neither 1 1 nor onto by just eliminating all those three options. Okay, but I will provide you why it is not 1 1. Okay, I will provide you information for also for that why it is not 1 1. Okay, so just use this one. Okay, I am writing it here. If you take P as 1 and Q as 3, okay, yes, okay, if you take P as 1 and Q as 3, what you are getting, not 1, just take it as 10 to the power 3. Okay, so you are taking P as 10 to the power 3, that is 1000, and Q as 3. You see that their GCD is 1 and everything that is written here is satisfied. Okay, so you can write f of x. What is your x? P over q. Okay, so your x is P over q, that will directly imply 10 to the power 3 over 10 to the power 3 is equal to 1. So if you are putting your x as 10 to the power 3 over 3, what you are getting? You are getting your result as 1. Now just replace this by, just put P is equal to 10 and Q is equal to 1. Okay, you will see that your GCD is 1 and every condition that is written here is already satisfied. So your function value at 10 over 1 is also 10 over 10 to the power 1, that is 1. So for two different values, okay, for 1000 over 3 and for 10, you are getting the same answer. Okay, so this is your codomain, that is real, and this is your domain. So for two different values you are getting the same answer, so that directly implies that your function is not 1 1. Okay, you don't need to check this because you have already checked that it is not on 2, and by discarding all these options you are getting the answer, but for the sake of knowledge you can see this. Okay, so thank you guys, and now wait. Now you if you are interested in just seeing the proof of these two important note, you can just go into the description and you will find the link for the video that will prove these two important notes. Okay, so thank you guys. The paper, so let us firstly read it. Let s is equal to x comma y such that x square plus y square is equal to 1 over n square, where n belongs to natural and either x belongs to q or y belongs to q. Here q is the set of rational number and n is the set of positive integer. Then what you have to check, then which of the following are true. Okay, that this is what you have to check. Now let us firstly see this thing, that what your set S is actually. Your set S is actually containing all those members, okay, all those tuples x comma y, such that their square is 1 over n square. N belongs to q and either x belongs to q, no, n belongs to natural, or either x belongs to q or y belongs to q. This is what you have to choose. So your set S is exactly like this. Now what you see, that x belongs to q or y belongs to q basically means that at least one of the tuple between x and y has to be a rational number. Okay, both the tuple cannot be irrational. This is what this thing is saying. Now from this thing what you can conclude, that your S set will always be a subset of q cross q complement cross, or not cross, it will be union q complement cross q union q cross q. Now if you have studied the topic countability and uncountability in the topic analysis, then you must have studied this thing, that the set of irrational is actually uncountable and the set of rationals is countable. Okay, this is what you know. Now this set is actually containing q complement part, therefore this thing is irrational, because if you fix one thing from here, okay, let us fix q from here, let us fix an element from q here, then you can vary that element to the set of whole irrational. Okay, so let us just think over it, that this set will be uncountable. Okay, so this will be exercise for you. So let us, what I am saying, that you can prove it in this sense, that let us fix a from here. Okay, now what you see, that you can vary this a with x, where x belongs to q complement. So this tuple has exactly the same cardinality as the set of irrational, because this a is fixed, so x is moving in q complement, so this set is actually having the cardinalities as the same set of irrationals. Since irrational is uncountable, therefore this thing is uncountable. Okay, what I mean to say that this thing is uncountable, and the thing next written to it is countable. This thing is uncountable also, similar to, okay, what I have given a proof for this thing is will be valid for this thing also. Now the third one is countable, because you know Cartesian product of two countable set is again countable. Since Q is countable, therefore it is countable. Uncountable union uncountable, union countable is uncountable. Okay, so S is a subset of uncountable set. So from this thing you cannot predict that what S will be. Okay, S can be countable, S can be finite, S can be empty. So writing this thing, I have written this thing because I want to make you understand this thing, that S will look like this. Okay, from this we cannot conclude anything about the countability and uncountability of the set. Now coming for the option 1, your option 1 is saying that S will be finite. So let us take X to be 0 and Y to be 1 over n. Now you see that X is 0 and Y is 1 over n, so both the coordinate belongs to rational numbers, so this will imply that X comma Y belongs to your S set. Okay, also x square plus y square is 1 by n square. Okay, therefore, okay, after doing this, this will be concluded that X comma Y will belongs to S. Now you see that this thing, if I take it as a set A, now this thing 0 comma 1 by n such that n belongs to natural number is actually a subset of S. Now this thing has the same cardinality as the set of natural number, because this has a 1-1 correspondence with the set of natural number. For each natural number there exists a point in A, therefore this set has 1-1 correspondence with the set of rationals, with the set of naturals. So this thing is, from here what you can conclude, that this thing is countably infinite. Okay, this is what you can conclude it from here, that this set is countably infinite. Now since this thing is subset of S, so S cannot be finite from here, so your first option is incorrect. Now coming for the option 4, fourth option is saying that S is empty, so 1 and 4th are done from here, that both are false. Okay, now coming for the option 2 and 3rd, there is a 50-50 chance, okay, that S can be countable and S can be uncountable from here. Okay, so we have to check that thing. Now let us take first case. Okay, case number 1. Okay, this case, if X belongs to Q and Y belongs to Q complement. Okay, now X belongs to Q and Y belongs to Q. Also, if this tuple belongs to S, then it also has to satisfy this thing, X square plus Y square is equal to 1 over n square. So this will imply that Y square must satisfy 1 over n square minus X square. Now this number is actually a rational number, and this number is also a rational because X belongs to Q, therefore X square belongs to Q. So this whole thing is actually belonging to Q. This whole thing is actually a rational number. Okay, so from this thing what you are concluding? You are concluding that you don't have to take the whole set of irrational. Okay, you don't have to take the whole set of irrational. You have to take all those irrational member whose square is a rational. Okay, you got my point? You have to take all those irrational from the Q complement whose square is rational. So this will imply that Y will always be of type P over Q. Okay, sorry, root P over Q. So from this thing what you are concluding, that your Y will always be of type root P over Q. Okay, where P over Q is a rational number. Okay, this is what you are concluding from here. Now in your case 1, let us take this thing as, okay, let us take this thing as X comma Y such that X belongs to Q and your Y is of type root P over Q. Okay, so this is your A set. I am defining this set to be A. Now this A set can be replaced by, okay, what I am doing, this thing what I have written earlier can be replaced by, okay, I will write that thing here, that this thing can be replaced by Q cross A. You don't have to take the whole Q complement. Okay, you can just choose A and then all the hypotheses will be true. So this Q complement set can be replaced by A and this will be still be true. Okay, I will add the things up here, but you will see that this Q complement set can be replaced by A. Now you see, for every P over Q there is a Y. For every P over Q there is a Y. That means this A set has cardinality Q cross Q. You are getting my point? Your X belongs to Q and Y belongs to Q, but Y is of type root P by Q. Therefore you can say that Y is varying over the set of rational. Y is varying over the set of rational means this set has a 1-1 correspondence with the set of Q cross Q. Okay, with the set Q cross Q. Therefore this set is countable. Now you know this thing, that this set is countable, countably infinite. Okay, this thing is countably infinite. This is what you can conclude. Now coming for the case 2. Okay, I am looking on this case now. Now you have to take your X from the Q complement set and Y from the set Q. Now what you see, that X square plus Y square is actually 1 over N square. Now from this thing what you are concluding, that Y square is 1 over N square minus X square. Okay, okay, I will not take Y here. From this thing what you are concluding, that your X square must be 1 over N square minus Y square. Now with this Y belongs to Q, therefore Y square belongs to Q, and 1 over N belongs to Q, therefore 1 over N square belongs to Q. Therefore this thing is actually belonging to Q. Now you are taking X from the set Q complement. Okay, you are taking X from the set Q complement, that is set of irrational. But you don't have to take, again you don't have to take all the set of irrational. What you have to choose? You have to choose all those members whose square is a rational number. Okay, so X will be always of type this. Okay, X will always be of type this from this thing. Okay, similar to the case 1. Case 1 and case 2 are similar if you interchange X and Y. So your X is always of type P over Q. Okay, now let us consider this set to be, okay, let us consider this set to be B, where X comma Y such that X is equal to P over Q, is of type P over Q. Okay, where P over Q is a rational and Y belongs to Q. Now let us take this set as your B set. Now you see that X is actually a irrational, but it is always of type P over Q. So you can say that X is actually having 1-1 correspondence with the set of rational and Y belongs to Q. Therefore you can say that this B set has a 1-1 correspondence with the set of Q cross Q. Okay, you are getting my point? This set has actually 1-1 correspondence with the set Q cross Q. Therefore what you can do is you can replace this Q complement set by a little bit smaller set that is known as B. So I will write B union Q here. Okay, now you don't have to check the another thing. Okay, that case third, that X belongs to Q and Y belongs to Q, because if X belongs to Q and Y belongs to Q, then you can just simply write them here. Okay, now S is always a subset of this thing. Okay, firstly you have taken a bigger bound for S, now you have taken a smaller bound for S. Now this set is countably infinite. Okay, so this will be a Cartesian product. Now firstly, you know, what do you know? That product of two countable set is countable. Okay, this is what you know. Product of two countable set is countable. Therefore Q cross A is actually countable. Now B cross Q will be countable because this one is countably infinite. Q cross Q is countable. You know this from the very beginning. Okay, because Q is countable and Q is countable, therefore Q cross Q is countable. So this whole thing is countable, this whole thing is countable, and this whole thing is countable. So you know, what do you know? That countable union of countable set will be countable. Therefore S is a subset of a countable set. Okay, so S is a subset of a countable set. Therefore what you can think over here, that S will be countable. S cannot be uncountable. From this thing we are concluding this. So third one is incorrect. So this is a little bit tricky, but I am using the formal proof, but in the exam you can just think over it, and just by seeing the question properly you can just tick the second one. Okay, but I am explaining it to you, therefore it is taking long time, but you have to be little bit you can say correct, okay, while giving the proof, while you are explaining something to anyone. Okay, so thank you guys. Question from the topic set theory. So let us firstly read this question. Consider a function f such that r to r. So r is a real valued function, f is a real valued function. Then which of the following are true? So your first option says that f is not 1 1 if the graph of f intersects some line parallel to x-axis in at least 2 points. You're getting my point? So what your option 1 actually says, okay, I'm just trying to show you this option with the graph so that you can get intuition about this question. It says if your graph is intersected by a line parallel to x-axis at least 2 points, so let us say this is your graph and you take a line parallel to x-axis, let us say this is line y is equal to c, so it intersects the graph of f at least twice. That means let us say this point is x is equal to a and this point is x is equal to b. So this coordinate will be b comma c and this coordinate will be a comma c. So from here what you are getting? You are getting that f of a is c and f of b is c. That means your graph is not, since a and b are distinct, that means your function f is not 1 1. So this is what your question is saying, that f is not 1 1 if the graph of f intersects some line parallel to x-axis. Now let us do this thing mathematically. Okay, so firstly I will introduce with the graph. What is the meaning of graph of f? Graph of f is actually a set that consists of these coordinates, okay, such that x belongs to r. So this is the definition for graph of f. Now what is given to you, that f intersect a line parallel to y-axis. So let us take a line. So I am taking a line which is parallel to x-axis. So this is your line which is parallel to x-axis. Now it says that it intersects graph of f at 2 points. That means what is the meaning of that? That there exist x1 and x2 such that, okay, f of x1 is equal to c and f of x2 is equal to c. This is the meaning of intersection, right? This graph is intersected by this line at least 2 points. That means this thing is happening. So from here what you are concluding, that this is not 1 1. Okay, this is very easy question, you can think it yourself. I am just doing it mathematically. So therefore your first option is actually correct. Now your second option says that f is 1 1 if the graph of f intersect any line parallel to x-axis in at most 1 point. Okay, so for this I will show you a note. Okay, so this is known as the graphical test for injectivity and surjectivity. Okay, so what is that graphical test? It says f is 1 1 if the graph of f intersect line parallel to x-axis at most once. So this is the test for the injectivity, this is the graphical test for the injectivity, and this statement is exactly copied here. Therefore this must be true. Now let us see third option. It says f is surjective if the graph of f intersect every line parallel to x-axis. And now let us see the test for surjectivity. It says f is surjective if the graph of f intersect every line parallel to x-axis. So this thing is actually copied here. So third is also correct. Now fourth one says that f is not surjective if the graph of f does not intersect at least 1 point, at least one line parallel to x-axis. Okay, that means I will solve now fourth option. What question says that graph, let us take a line parallel to x-axis. Okay, so line parallel to x-axis will be like y is equal to c type. Now it says that your graph is not surjective if the graph of f does not intersect at least one line parallel to x-axis. What does that mean to you? This means, now let us suppose do it very simply. Let us say this is your graph. Okay, now you see this thing, your line y is equal to c is never going to intersect this graph. So this, this graph is actually not surjective because it's not taking the value after this point. So graphically you can do it directly. This is obvious from here that if there exists a line such that, if there exists a line parallel to y-axis such that the graph of f is not intersected to that line, then that will not be surjective, right? Now let us do it little bit mathematically. Okay, so let y is equal to c be a line such that it does not intersect the graph of f. That means there does not exist x such that fx is equal to c. You are getting my point? So this means c belongs to R, but c has no preimage. So therefore it is not surjective. You can do it mathematically or either you can do it graphically. Okay, so therefore your fourth option is also correct because it says f is not surjective if the graph of f does not intersect at least one line parallel to x-axis. So this was a very easy question. Just you need to remember these graphical tests. These are called tests, but they are not actually tests because they are very obvious. Okay, if you will think over it, they are very obvious to see why these tests are correct. Okay, so thank you guys. So this question basically needs the knowledge of analysis as well as the knowledge of number theory. So if you don't know number theory, then there is nothing to worry about. You have to just remember few statements and then you will be able to solve this question. Okay, so let us read question. Let Pn denote the nth prime number when we enumerate the prime number in the increasing order. Okay, so you see Pn is the nth prime number. That means 2 is the first prime number, 3 is the second prime number, and 5 is the third prime number. Okay, so we are taking Pn as a sequence in the increasing order of prime. So what they are saying, they are defining a set S. The set S is given by Sn is equal to Pn plus 1 minus Pn. That means set S consists of the difference of two consecutive primes. Okay, then we need to check which of the following are correct. So let us start. What you see first here, that they are talking about the supremum of the set. Okay, so you need to see what are the elements in the set S. The set S consists of the difference of successive primes. That means if first option is correct, then the difference of the successive prime, that there should exist two successive prime whose difference is infinite. Okay, you understand what I mean? What I am saying, that if you want your first option to be correct, then there must exist two successive primes. Okay, two successive prime such that their difference is infinite. Okay, so I am writing a note for you. You just have to remember it or you can prove it. Okay, so what I am saying, there exist primes such that there exist not primes only, there exist consecutive prime. Okay, there exist consecutive primes such that difference between them is infinite. Okay, so this one is the note that you have to remember. Okay, so I will give a short proof of it. So you have to show that there exists prime so that difference is infinite. So before that, let us consider a number n. Okay, I am considering a number n that belongs to natural number and I also belonging to natural number. Okay, such that n is greater than equal to I. So if n is greater than equal to I and both belongs to natural number, it will directly imply that I must be a factor of n factorial. So I divides n factorial. Okay, So since I divides n factorial, that will directly imply that I must divide n factorial plus I. Okay, so these three statements are consecutive. Okay, if this happen, then this will happen and this will happen. Okay, now let us take a number n factorial plus 2. Okay, so I am taking this number and I am taking another number n factorial plus n. Now what you see that if your n is large enough, okay, if your n is large enough, then 2, okay, 2 will always divide n factorial plus 2. Okay, what I mean to say that this number is divisible by 2. Now I will take another number, I am making it as a sequence. So since n is large enough, that means n is always greater than 3. Okay, from this one you can directly say that 3 will divide, okay, 3 is going to divide this. Now you see, since n is large enough, so n must be greater than 4, that means 4 must divide this one, okay, and n must divide this one. So we got a sequence. Okay, so we got a sequence of n minus 1 consecutive composite number. Okay, so what I am saying that if n is large enough, then we can get a sequence of n minus 1 consecutive numbers. Okay, consecutive composite numbers, consecutive composite numbers. So you see, if n goes to infinity, then difference infinity minus 1 is infinity. That means you get a sequence of consecutive infinite composite number. So if I am supposing p1 is a number here and p2 is a number here that are successive primes. So what I am saying that p1 and p2 are two successive prime which are on the left side of this sequence, and this one is on the right side of this sequence. That means between these two prime there exist infinitely many composite number. So there does not exist any prime which lie between them. So what you see from here, that the difference between p2 minus p1 is infinite. So that will directly imply p2 minus p1 is infinite when n tends to infinity. Okay, so what will this imply? This imply supremum of S is infinite. So your A option is actually correct. So I have proved A option. Now from this one you can directly say that limit superior is infinite. So B option is also correct. Okay, now coming for the C option and D option. Now what C option is saying that infimum of S is 1. So you see, what will be the infimum? Infimum is the least number that is present in the set. So if you see the sequence of prime, then you will find out that these are the only two consecutive prime that has difference 1. After that difference increases, but after that this difference is always greater than 1. Okay, so these are the 2 and 3 are the two consecutive prime whose difference is 1. That means 1 belongs to S and that is the least number. So infimum of S must be 1. Okay, so C is also correct. Now coming back to the D option. Okay, so far we have not used any number theory. Okay, but for the option D you must know something, some number theory. Okay, for the option D. So what I am going to use from number theory is a theorem, or you can say conjecture. Okay, so this is known as twin prime conjecture. Okay, this you must know to solve the option D. What twin prime conjecture suggests? That there exist infinitely many twin prime. Okay, so this is what twin prime conjecture suggests. Twin, what is the meaning of twin prime? Twin prime means the difference between two prime. Okay, so there exists, this imply there exist infinitely many, okay, consecutive prime such that their difference is 2. Okay, so twin prime means consecutive prime whose difference is 2. So you see, you have infinitely many consecutive prime whose difference is 2. So in the sequence Sn, if you are trying to write the sequence Sn, the first member of the sequence must be 1. After that it is 2, after that it is 4. But what twin prime conjecture is guaranteeing us that 2 will occur infinitely many times in this sequence. We don't know how many terms 2 will occur, but we know that 2 must occur. Okay, so you see 2 is repeated infinitely many times here. So 2 must be a limit point, and it is the least limit point you see. Okay, since 1 is occurring only once, so 1 cannot be a limit point. Limit inferior is actually the least limit point. So 2 you see is the least limit point. Okay, so D, okay, so this will imply limit inferior of Sn is 2. So automatically D is correct. Okay, so your D option is also correct. A is correct, B is correct, C is correct, and D is correct. Okay, so thank you guys.
CSIR net December 2019. So this is question number 22 and it is from the topic analysis. So let us have a look on this question. It says, which of the following set is countable? So you have 4 options, that means you have 4 set for which you have to determine the countability. So your first set is the set of all functions from Q to Q. Your second set is set of all functions from Q to 0, 1. Your third set is set of all functions from Q to 0, 1 which vanishes outside a finite set. And your fourth option is the set of all subsets of n. So these are your 4 options. Okay. So firstly, what I will do, I will introduce you a theorem. Okay, I will not say a theorem but a problem, which is a very famous problem from the topic countability. If you have done this topic countability from the course analysis, then you must have done that problem. Okay, so I will take it granted that you have proved that problem. Okay, without that thing, it will be little bit difficult to prove it here. That will make this video very long and I don't want that. So let us begin. So this is the problem that I am talking. What it is saying? It is saying that the set of all functions from n to 0, 1 is uncountable. Okay, that means if you have a set like this, okay, if you have a set like this, f such that f is a function from natural number to this set, right? Then this problem is suggesting us that this set is uncountable, right? Now what you know, natural number is actually a countable set, and you know rationals are also countable. Now since n and q have same cardinality, that means if you have a set which consists of all those functions from q to 0, 1, that means for using this problem I can directly say that that set will also be uncountable, right? So that means if you have this is option number 2, the set of option number 2, that is f such that n to not n, sorry, this is q to 0, 1, right? This set is uncountable using this problem, right? Okay, now coming to the option number 1. Okay, before coming to the option number 1, I will just give you an example. Okay, so suppose you have a set like this 1 2 3 4. Okay, and you are trying to find out how many function can exist between these two sets. Okay, let us say this is your domain D and this is your codomain C. Okay, so what is the formula for that? You have done it in the intermediate course. Okay, so you know that 2 to the power 2. This number is actually representing the number of functions between these two. Now, if you will increase this domain, not increase, if you will add some more element to this domain, then what will happen? Number of function will actually increase, right? Okay, number of function will actually increase. Now, in this not domain, okay, if you will add an element to its sorry, I was confused in that. Okay, now I'm correct. If you will add an element to its codomain, then what will happen? Number of function will still increase. Okay, and number of function will be given by this formula, right? So 3 to the square, and this is 2 to the square. So this is 4 and this is 9, right? So that means if you will add more element to the codomain, then you will get more number of functions, right? That means if you have a set like this, f such that f is a function from q to 0 1, this set, then this set will be a subset for this set. You're getting my point or not? This set is actually a subset of this set. Now you have already proved that this left hand side set is uncountable, right? Now since it is uncountable, that means since it is a superset of this set, that means this will also be uncountable. You're getting my point or not? What is my basic point is that if you will increase more number of element, okay, if you will add more number of element to the codomain, then your number of function will actually increase. Okay, the same will happen for the domain also, but in our case domain is not there. Domain remains same, so I have to remove this thing. Okay, now your second option is incorrect, and what I have proved that your first option is also incorrect. This is what I have proved. Now coming to the fourth number option, what your fourth number option says, that power set of natural number, right? Power set of natural number. Now since you have done this topic countability and uncountability, I'm assuming that, so I'm not going to prove that why it is uncountable, but it is a very trivial fact there that it is uncountable. Everybody knows it, so I'm not going to prove it. Okay, this is a well-known fact. If you heard the word uncountability, then uncountability actually means power set of natural number, right? So I'm not going to prove it. This is also uncountable. Okay, so this is fact. Fourth is incorrect, and second and 1 are also incorrect. That means third is correct. Now what I need to do, I need to prove this third option, right? Now I will prove it here. For third option I will write the proof. Okay, now before starting this proof, what I will remind you two theorems. Okay, so what are those theorems? Let us see. So it says the number of finite cardinality subset of a countable, okay, I will say it again. Number of finite subset of a countable infinite subset is countably infinite. Okay, that means if you have a countably infinite set, then number of subset which are finite will be countably infinite, right? That means I will give you just example for that. If you have this set natural number, right? If you have this set natural number, then if you are collecting all those subsets which are finite, then that collection will be countably infinite. Okay, this is what this theorem is suggesting us. Okay, another theorem, let us see. It says countable union of finite set is again countable. Okay, these are the two theorems which will be needed to prove this thing. Okay, now it says the set of all functions from q to 0 1. Let us, okay, I'm not proving this thing very rigorously, I'm just giving you an idea. Okay, I will just hint you to prove it. Let us suppose this is your q and this is your 0 1. Okay, now what this option says, it says the set of all functions from q to 0 1 which vanishes outside a finite set.
Now suppose you have a finite set inside it. Let us name it alpha 1, alpha 2 up to alpha n. Suppose this is your finite set. Okay, this is your finite set. Now it says you have to take all those functions which will outside this finite set. That means outside this finite set you will get image 0, and from this set you are getting 1 as your image. You are getting my point? So if I want to count those functions, that means those functions will totally be dependent on this finite set. Okay, if you will vary this finite set, then you will get a different function. Okay, what I am saying, that if you have another set here, let us say beta 1, beta 2, let us say a set with 2 elements. Now this set, a function which is not vanishing over this set beta 1 and beta 2, and it is vanishing on the rest, that will be a different function from the function that we were talking earlier. That means this alpha 1, alpha 2 up to alpha n, the function which is not which has image 1 over this set and image 0 over the rest, is a different function from that. You're getting my point or not? So if you want to calculate or count those functions which will vanishes outside a finite set, then you have to count all the finite subsets of Q, right? Now what we have done in the theorem, that for a countable set, number of finite set is countably infinite. Okay, countable actually means countably infinite. Okay, now this is countably infinite, that means number of finite subset of it will be countably infinite, right? You are getting my point or not? So you are actually collecting all those functions. Okay, you are collecting all those functions, that means you are collecting all those sets. So using that theorem, what you can say, that this thing will be countably infinite. You are getting my point or not? I will say it again. It is little bit confusing here. What I am saying, if you have this set Q and f is a function from here. Okay, let us say this is your finite set and this is your code domain. I will make it again. This is your Q and this is your 0 1 set, right? Now this is your finite set. Now a function, if a function, let us say this is your function f has image 1 over this set, and for the rest it has image 0. Now for this function, image for this finite set is 1 and for the rest it is 0. These two functions are actually different, right? These two functions are actually different. So what makes them differ? This set actually makes them differ, right? That if you will change this set, that means you will get different function. So from here what you can conclude, that all those function, number of such functions will be totally dependent on the number of finite subsets, right? So from here what you can say, that the set of all functions from Q to 0 1 which will vanishes outside a finite set are countably infinite. Okay, so third option is correct. Okay, it is little bit tricky to make you understand this thing, but if you will think it yourself, you will get it, right? So first, second and fourth are incorrect and third option is correct. Okay, so thank you.